Following on from the previous video, which was just an introduction into congruences, here we're going to be using congruences to establish rules of divisibility. But first of all, a reminder of some of those rules of divisibility. Simple one, the last digit divides by 2. Even numbers. The digit sum, when you add up all the digits in the number, it turns out to be a multiple of 3. The last 2 digits form a number which divide by 4. Easy one, ends in a 0 or a 5. The rules for divide by 2 and divide by 3 apply. In other words, it has to be an even number, and the digit sum has to be a multiple of 3. Divides by 7? Not yet. The number formed by the last 3 digits divides by 8. Same as the 3. Digit sum is a multiple of 9. Easy, ends in a 0. Divide by 11? Not yet. Develop that at the end. Rules divide by 3 and divide by 4 apply. The digit sum comes to a multiple of 3, and the last 2 digits form a number which divides by 4. Now, what about these two? Get them later. And what about this business about congruences? How do congruences establish all of these rules? Now, I'm not going to go through them all. I'll just pick out a couple. I'll pick out divide by 2, divide by 8, divide by 9, and then do the divide by 7 and 11. But first, a little check on those divisibility rules. 1, 2, 3, 4, 5, 6. There's a nice simple number. What divides into that? Checking the rules. What about divide by 2? Is it even? Does the last digit divide by 2? Yes, it does. What about divide by 3? What's the digit sum? Well, you've got 10, 15, 21. The digit sum is 21. That's a multiple of 3, so it divides by 3. What about divide by 4? Do the last 2 digits, 56, divide by 4. 4 into 4, 5 goes 1, 1 over, that's 16, so that's 4. So yes, it does. What about divide by 5? Does it end in a 0 or 5? No. What about divide by 6? Well, does 2 and 3 apply? Yes. What about divide by 7? We don't know that one yet. What about divide by 8? Is the number formed by the last 3 digits divisible by 8? 8 into 45 goes 5, 5 over, into 56 goes 7, so yes. What about divide by 9? Is the digit sum a multiple of 9? No, it's not. What about divide by 10? Doesn't end in a 0. What about divide by 11? Haven't established that yet. What about divide by 12? Well, does 3 and 4 apply? Yes, it does. Now the congruences part. Now, where congruences are useful is whenever you've got something like either if some number is congruent to 1 mod some base, or if some number is congruent to 0 mod some base. They're very handy ones to arrive at because they can disappear from the evaluations. If n is congruent to 1, that will disappear from a multiplication. So that's a handy one to aim for there. And if n is congruent to 0, that can disappear from an addition of terms. So here, looking at numbers that divide by other numbers, well, the first thing is this, a bit of notation. If n stands for some number, I'll just put down some of the digits here, then I'll call the digits this. That first part, that can be digit 1, digit 2, digit 3, all the way to digit n, so that's digit n minus 1 and digit n minus 2, and I can't be bothered doing that, so I'll put some more dots in. And the block of digits within that number, I'll name according to how far it goes. So if I call that A with an n minus 1, it means the number formed by taking just the first A n minus 1 digits. Similarly, but not strictly speaking following the same protocol, the number formed by the digits at the end I'll call the last group, but I'm not going to call them n. For instance, this group here, I would call that L3, because you're not going to be interested in more than about 1 or 2 or 3, because otherwise you're just involving the whole number. Right, a check then. What about divides by 2? What's the rule for divides by 2? Well, if 2 divides a number, that means that that number must be congruent to 0 mod 2. And I'll split that number up using these terms here. So that means that if I take the first group, a n minus 1, to form this number, 10 times that group, because it starts in the tens column, plus the last digit forms the number, so that should be congruent to 0. Mod 2. Now obviously, this term divides by 2. 10 anything is a, I'll put that to the side, but I'm not going to mention it again. 10 of anything, 10 a to the n minus 1 is obviously congruent to 0 mod 2, which means this just boils down to dn should be congruent to 0 mod 2. And the rest of the number doesn't matter at all. So that's equivalent to saying the last digit is a multiple of 2, or divides by 2. Very quick. Similarly, what about divide by 8? Well, 8 will divide into a number if that number is congruent to 0 mod 8. And I'll split the number up again. So that number can be split into, now, whereas previously these column headings obviously go 10 times each time, this second biggest group, if you like, would require 10 times it, and 10 divided by 2, so obviously that was going to work. The next one would be 100 times it. That doesn't divide by 8. So if I went to this group here, not a of n minus 1 or minus 2, if I went to a of n minus 3, so that leaves the last 3 here, I would need 1,000 of those to re-establish the number, and then add on that group at the end. So what that says is, this number's formed by this group at the end, plus the part in front, but of course the part in front would have to be multiplied by 1,000 to keep it in the correct column headings. Mod 8. That divides by 8, so this term disappears, so you just end up with L3 is congruent to 0 mod 8. And what that says is the number formed by the 3 digits at the end has to be a multiple of 8. You could develop that further, but it's not worthwhile. That would be the simplest way for it. You could split L3 into 100 of dn minus 2 plus 10 times dn minus 1 plus dn to be congruent to 0 mod 8. I'm just going to stop with this one though, because that's the simplest rule. Just to see if there's a more convenient pattern here, but there's not really. I'd have to split that into multiples of 8, so that would have to split into 96 lots of dn minus 2 plus 4 lots of dn minus 2, then that disappears. I'd split that into 8 lots of dn minus 1 plus 2 lots of dn minus 1, so that disappears, plus dn being congruent to 0 mod 8. Then those terms disappear, but then what this says is, if you take the last digit and add on twice the second and add on 4 times the third one, it should produce a number that's a multiple of 8, and that's not really worth it. You're as well just sticking with this one. There might be cases where that jumps out at you with certain number configurations, but generally that's going to be the rule then. The number formed by the last 3 digits is a multiple of 8. Now divide by 9. Now from 9 and 11 and 7, I'm not going to be interested in the group in the end anymore. This is a bit lengthy though, so I'm not going to go all the way through it because it depends how many steps there are. So basically it would be this. 9 divides a number if n is congruent to 0 mod 9. Then same steps as before, let's start splitting the groups up. 10 lots of a n minus 1 plus the last digit has to be congruent to 0. Splitting that up. 9 a n minus 1 plus a n minus 1 plus dn is congruent to 0. Which means that I've got a n minus 1 plus dn is congruent to 0. Now I'll name this line. That's the line that's got n minus 1 in it. Taking the similar step to this, breaking up a n minus 1 now, would give you this next group. 10 a n minus 2 plus d n minus 1 plus dn is congruent to 0 mod 9. And that would just be starting at this point. So obviously that would split into the 9 and the 1 again. So that would come all the way down to a n minus 2 plus dn minus 1 plus dn is congruent to 0. So that's the line that reads, I've got down to term n minus 2. And similarly, following that pattern, until you got down to the line where it was just the number 1, you would have eventually that A1, which is the same as D1, so D1 plus the succeeding digits, D1 plus D2 plus D3, all the way to Dn minus 1, Dn must be congruent to 0 mod 9, and that says the digit sum. Digit sum divides by 9 or is a multiple of 9. Need a bit more room for this one. Now what about those missing 2? We'll do divide by 11 first of all, same as before. 11 will divide a number if that number is congruent to 0 mod 11. Now splitting that up. So a of n minus 1 is the group before it. If I want to add it on to the last digit, I'll have to take 10 times it to keep its size correct. So 10 times an minus 1 plus dn has to be congruent to 0 mod 11. Splitting that, or constructing rather, an 11 so that it can disappear, that'd be the same as saying 11 an minus 1 minus an an. That's a bit naughty there, having these negatives in this part where you're dealing normally with positive integers, plus dn has to be congruent to 0. Now, that term will disappear, leaving me with these two, but then by doing 0 minus both sides, I can change the signs into an minus 1 minus dn is congruent to 0 mod 11. Now I've got an expression, I'll call that's the line that took me to n minus 1. Doing the same again, so I'm going to be repeating these groups here. So now I'm just going to be repeating this. So I can split that, taking that group there in one step, I would have to have 10 of the previous block, that's the n minus 2, and that would isolate the digit dn minus 1 minus the dn has to be congruent to 0. And the same way as that, split into this and into that, I would have, I'll put this line down first of all, I'd have 11 of them minus 1 of them, so I'll put that in. an minus 2 plus dn minus 1 minus dn should be congruent to 0. And then doing 0 minus both sides, I've got an minus 2 minus dn minus 1 plus dn is congruent to 0. So there's that similar calculation stepping in 1. So that took me to the n minus 2 level. Doing the same again for n minus 3 in one go would produce then an minus 3 minus dn minus 2. That was what would come from this. Plus dn minus 1 minus dn should be congruent to 0. And from there you can see that eventually by the time you get down to the first term, which is a1, which equals d1, you'll end up with d1 minus d2 plus d3, whoops, minus and so on until you get to the last term. Should be congruent to 0. And then it all depends what n is, how many terms there are, whether that's a plus or a minus there. So we'll have to put a negative 1 multiplier in. And you can see that the even terms, according to this, should be a negative 1. So whatever that is, if I take 1 off of it, that'll be the correct sign. So what does this lot say? Well, notice you've got alternating terms are positive and negative. So if you add up the positive terms and add up the negative terms, those are alternating ones, the difference between them should be 0. And that's the rule for divide by 11. The difference in the digit sum of alternate terms is a multiple of 11. Now the bad penny. Now the divide by 7. 7 will divide a number if that number is congruent to 0 mod 7. Same technique. So let that number equal a to the n minus 1. So it'll be 10 lots of that plus dn. That has to be congruent to 7. It's congruent to 0 mod 7. Now the problem here is going to be this 10 isn't close to 7. It worked out nicely for 9 and 11 because 9 plus 1 made the 10, so you had all those positive terms. But 10 is 11 minus 1, so you had those alternating terms. Here, if I split that up, I'd have to say, well, I'll split it into 7 lots of that, so that can disappear, because the modulus of that is 0. But that would then be plus 3 lots of A, plus dn is congruent to 0. Now, that'll disappear, and that's not much of a rule. If you do 3 times the block and add the last digit onto it, it should divide by 7. Can we tidy it up a bit? This is a bit like we've got to play with these numbers now. It's like they're filling those jars to get so many litres in one of them. What you could do is double both of those. 6an minus 1 plus 2dn would be congruent to 0. That's just using the normal rules. You can multiply both sides by some number. That's close to 7 now. So that's like 7a to the n minus 1 minus an a to the n minus 1 plus 2dn is congruent to 0. Now that will disappear because that's a multiple of 7, so that is congruent to 0. And subtracting both sides from 0 can flip that over to a to the n minus 1 minus 2dn should be congruent to 0. Now this big block here could get repeated because that's us got down to the line n minus 1 now. The only problem is when I repeat this, things will start to get doubled. That might be the best you can get. But of course that says the remaining block. So what you could do here is just use this as an algorithm. Double the last digit and take it off. Is that a multiple of 7? Don't know. We'll now have arrived at a smaller number. Double the last digit and take it off. Have I arrived at a multiple of 7? And so on until you recognise the final number as being a multiple of 7 or not. If we continue with this, it's going to go into a mess. I'll go through it quickly. So that means we've got, splitting that up again, I've got 10 a to the n minus 2 plus d2 minus n minus 1 plus 2dn should be congruent to 0 modulo 7. Now that line can get repeated here and it will end up with this expression, but notice there was a doubling involved. So when this does come down to this part, 3 of them, 3an minus 2 plus dn minus 1. I then want to double it, but as soon as I double that, I've got to double the whole side. That'll then become 4. So the next line following the pattern here would be a to the n minus 2, and of course the signs are flipping as well. It'll be minus 2d to the n d of n minus 1, but then plus 2, and that'll get multiplied. I'll put a squaring in there, of dn is congruent to 0 mod 7. That's the line n minus 2, and continuing that through in the same manner would eventually take you to, once it was down to a1, you would have d1 minus 2d2 plus 2 squared d3 minus and so on until you ended up with the last one, the dn, and that'll be 2 to the power n minus 1. Should be congruent to 0 mod 7. And of course it's alternating signs, but I can incorporate that into that. So negative 2 to the power n minus 1. But that's no use at all. The amount of work you would have to do that, to check if you arrived at a number that divides by 7, you're as well just dividing the number in the first place. So the best thing would be, the best you can do is just stick with this algorithm. So what's the rule for divide by 7? Subtract twice the last digit from the number block in front. I should have said repeatedly until the result is a recognisable, I should say, multiple of 7. Or not. So there is a rule for divide by 7, which might be useful in certain situations depending on the configuration of the digits. But is it worth it in general? Would it be faster than just dividing by 7? Well, one way to test that, well, sort of test it, would be to put down a number. So I'll find a number just by pressing buttons at random so I don't know what I've got. So here's a number. 667009. That should be a multiple of 7. Well, try it. Dividing first of all. So where's that start? So 7 into this, what would it be? Into 66 will be 9, that's 63, 3 over. Into 37 will be 5, that's 35, 2 over. Into 20 will be 2, that's 14, so there's 6 over. Into 60 will be 8, that's 56, so there's 4 over. And into 49 goes 7 exactly, so it works. We'll stop. Oh, can't see. No. I'm not convinced now. I'll just call that 26 seconds. Now for that test, that algorithm, subtract twice the last digit from the preceding block of digits. There we start. So that means take 18 from this. So 18 from that's going to be 66682. Take double that is 4 from this, 6664. Take 8 from this, 658. Take 16 from this, so that's going to be 49. It works. Oh, just press stop. Oh, 27 seconds. Well, I suppose that wasn't that conclusive. You could try that yourself. There's a wee game. Which is faster? But one thing's for certain, it's certainly not a quicker way. It's certainly not a very fast way of doing it. So the point here was, congruences gave me these rules, and you could try that yourself for the ones I didn't do. Use congruences to establish the rules of divisibility for the other ones.